Okay. Okay, many thanks for Professor Chen's opening remarks. Then let's move to our keynote speech session. We are honored to invite 3 excellent keynote speakers joining us. The first keynote speaker is Professor Chris Mee from Santiago State University, USA. He is the fellow of ICPES and the fellow of SAE. His speech title is Application of Wireless Power Transfer in Electric Aircraft, Railway, Ships, and Road Vehicles. Let's welcome Professor Mee.
Great. Thank you very much for your introduction. Let me share my screen.
Thank you.
Yeah. So it's a little bit tricky today. I'm not sure what exactly happened, but let's see why I can't share my screen. Okay, put it this way. I just want to make sure, do you see my screen? As a full screen now?
When can I see your screen?
Is it in presentation mode? Yes, okay, great. Well, again, thank you very much. And also thank you for the audience attending this conference. And it seems to be a very successful conference so far. We have so many participants and papers. So the conference theme is about power and energy systems. Now, one of the important issue is how we transmit power for different applications. So today, I will talk about how we can use wireless power transfer technology to power different things and different applications in terms of wireless power transfer. So just to give you a brief idea of where I'm from. So I come from San Diego State University, which is located in San Diego, California, of the United States. We are close to the US-Mexico border, which boosts the best weather in probably around the world. And the campus is located about 15 miles east of the city of San Diego. And just this year, we celebrated 120 years of anniversary for the university. So in today's talk, I will start to talk about the basic principle of wireless power. And then I will dive into the safety of wireless power, because every time in the early days when I present wireless power, I got to ask, is it safe to use wireless power transfer system? So I dive into that before I talk about some of the technology that we have developed at San Diego State University, which include the double-sided LCC topology for inductive power transfer, and also the LC-LC topology for capacitive wireless power transfer. So after that, I will explain the different applications of wireless power transfer, including the buses, trains, underwater robots, AGVs, and other applications. And finally, I'll give you some of my thoughts on where WEL stands for today in terms of wireless power. So let's start with the principle. So what is wireless power? Well, wireless power by definition is we transfer power via air gap. So there's no media other than the air, not like the traditional usage of electrical power. We plug it in, we conduct electricity through a cable. But in this case, we're transferring power via air. So you might see alternative names for wireless power. For example, some people call it contactless power or inductive power if you use inductors and coils. Capacitive wireless power transfer, if in the case we use electrical field to transfer electricity. And sometimes they also call this strongly coupled magnetic resonance or wireless energy transfer. The wireless power transfer itself, the idea was proposed in the very early days. Well, Nikola Tesla, which many of you probably know him, who is described as one of the smartest person in the world ever we have. So he proposed this, as you can see on the right hand, one of the displays while he was sitting in his laboratory in Colorado Springs. And at the bottom, you see the picture of Tesla and also the Warden Cliff Tower that he built, where he believed that wireless power can be realized in one day. However, over the last 100 years, it has not made a huge progress until the last about 10, 12 years. We have made a huge progress in this area. So we have made this possible. So look at that wireless power transfer. We have a couple different methods to study. So those included electromagnetic induction, radiation, and electromagnetic resonance. So the electromagnetic resonance is what we'll be talking today, which can also further classify into radio waves, microwaves, laser, and ultrasound from the radiation technology, which is not the focus of today. So today we're going to focus more on high power, high efficiency power transfer system, what we can use for example, electric vehicle charging. The application of wireless power transfer is very wide, from power levels at milliwatts to power levels at hundreds of kilowatts. And this slide shows the different applications of wireless power transfer. So on the left hand, you can see different applications, including light bulb, including electric vehicle applications, buses. To the left hand, to the right hand of the screen, you can see application in implanted devices such as a pacemaker. So this is a very wide range of applications. But how do we realize wireless power? So the basic principle of wireless power is very simple. It assembles the series of a transformer. Anybody in the electrical engineering area knows how transformer works. In the traditional way, if you look at the diagram on this slide, you can see that it assembles a transformer with mutual inductance and leakage inductance on the primary and the secondary. For a traditional transformer, which on the bottom left corner, you can see the leakage is about 2%. And they operate like 50, 60 hertz, or maybe at a high frequency, depending on application. Now, if you have this diagram, you know that the leakage is going to cost you about 1 to 2% of voltage drop if you apply an input voltage on the transformer's primary winding. So if we assume you input 100 volts at the input primary, you lose 2 volts on the leakage, you would get 98 volts on the primary winding. So if you get a 1-to-1 transformer ratio, you get 98 volts on the secondary. Now assume you lose like 2% again, you will really get about 96 volts on the load resistance. Assume there's a little bit loss on R1 and R2. So the voltage on the secondary is pretty high in comparison to the primary. Now, if you want, let's say 96 watts of power, you need 1 amp of current. So this is pretty much very high efficiency, 96, 97, 98%. So that's a traditional transformer. So what happens with wireless power, even though it is similar to a transformer, but the leakage is very high, typically about 80% or even more. So what happens is that if you apply 100 volts as a V1, you're going to see 80% drop on L1 sigma. Only 20 volts is left on the main winding. If you still take a 1-to-1 ratio, you will have only 20 volts on the secondary. Now you drop another 80% on L2 sigma. So eventually you only have 4 volts left for RL. For 4 volts, if you want to have 96 watts, you need something like more than 20 amps of current, 24 amps of current. Now, if you take that 24 amps of current, you square that, you multiply R1, R2, you get a lot of loss. So therefore, the system will not work. The efficiency will drop merely just less than 5%. So what do you do then? Now, fortunately, we have another impedance, which is a capacitor. The capacitor has a negative impedance. So ideally, if we add a C1 on the primary and C2 on the secondary, and we design the circuit, select the frequency and the capacitance such that the impedance of C1 cancels the leakage inductance of L1 sigma, and the impedance of C2 cancels the leakage inductance of L2 sigma, you see now the voltage of V1 will be 100% applied to the primary winding, except for a little bit drop on R1. Similarly, the voltage of the main winding is applied to the load, except for a little bit drop of R2. So therefore, you can realize a very high efficiency. We can solve the circuit very easily by using loop analysis, and we can get the current using no voltage, no parameters, and then we can calculate the input power, output power, and we can calculate the efficiency. Now, if we plot the efficiency as a function of frequency, you will notice that the frequency would change two reasons. One is that it will change with the parameter. So you have three curves, and you can see the frequency is different for the three different curves because they have different parameters. And also it changes for a single given curve. You can see that the efficiency is a function of frequency. For example, if you look at the blue curve, it reaches a peak at 90 kilohertz. Same is the red curve, it also reaches 90 kilohertz at the peak efficiency. And another red curve, it reaches peak efficiency at about 50 kilohertz. And the peak efficiency can be as high as 90% if the parameters are right, or it can be as low as 45% if the parameters are not selected properly. But if the frequency changes, the efficiency can drop dramatically to even less than 10%. For example, for the blue curve, if you reach around 120 kilohertz, right? So this means that we have to design a circuit to reach the resonant conditions so that we can reach the high efficiency. And also we have to select the parameters such that we can reach a high efficiency. Not only just a peak, but overall like 95 and more for the efficiency. So the previous circuit that you saw on the top left corner is series connection between C1 and L sigma on the primary, and also series on the secondary between C2 and L2 sigma. Now, based on resonance theory, is that when L2 and L2 sigma resonant, that forms our series connection. Now, we could also have a parallel connection. So if you see on the top right corner, L2 sigma is in parallel with C2, which means this is series parallel connection on the secondary, but series connection on the primary. So it forms a series parallel connection. And at the bottom left, you see a parallel and a parallel, and at the bottom right, you have parallel and a series on the secondary. So you have different the circuit combinations. Now, going to electric vehicle charger or any charger for that matter, not only you need the wireless transformer, which includes the windings on the primary and the secondary, but also you need auxiliary, not even auxiliary, but the main circuit, such as a DC to AC converter connected to the primary winding, and a rectifier connected to the secondary winding, where you can use convert that AC into DC to charge the battery. And you might need a DC to DC converter to control the operation of the circuit, and you also need a rectifier. You might need a PFC circuit. So all this is going to be needed for your overall circuit. And you also need, we also need communication between the secondary and the primary, because there's no direct contact between the secondary and the primary. Now, how would they do like the circuit? So if we go back to the circuit, you notice that between the primary and the secondary winding, there's a magnetic field. If you have a magnetic field in the air, which means it's going to create a field not only between the winding, but also between the two windings. So therefore, it's a natural question to ask, is it safe for such a WPT system? Well, in order to understand it, this was done many years ago, that we selected a power transfer system, and then we look at the different objects, like a human next to the vehicle, a cat, and a couple of metal pieces. And we started with a human that was lying down next to the car and see what happens. Well, we found that if the person's next to the car, if the windings are well shielded on the primary and secondary on the back, in fact, the B field is fairly small, like 27 microtesla. The E field is roughly 83 volt per meter at 85 kilohertz, which is this frequency is recommended by SAE GF2954 wireless charging standard. The the yellow on the top right corner is the requirement from certain standards. But our system only emits 1.36 microtesla and 2.83 volt per meter, which is like almost like more than one order less than the standard requirement, which means it's going to be pretty safe. And then we did some study of a human or the driver or the passenger sitting on the car seat inside the car. And then we found that, well, the B field is even smaller. We understand it because this is because of shielding. The E field gets stressed a little bit, but still way below the international standard. So we thought it was pretty safe. And then the third study we did was using a small animal to be placed or run into the transmission pad, on top of the transmission pad during charging. And we found, yes, there seems to be a problem that there's a B field increase to more than 1,000 microtesla. Now, because we know that a cat, a small animal, has blood and water, things like it in the body, so it will actually warm up the cat because the eddy current generated inside the body, and it will heat up the animal to about 40+ degrees C within roughly 30 to 40 minutes, which means it can create a sort of danger for the animal. It might kill the animal. Of course, it might also create some neurological or biological impact on animals, which we don't understand. And lastly, we did some study on the metal pieces, and we found that truly it is a problem with metal. And we found that the metal can actually heat up very quickly. Within a couple of minutes, the metal can be heated more than 100 degrees C. And if you place a piece over there for long enough, like 30 minutes, it will start to get burned, and which means it's going to ignite any dry object like leaves, paper, plastic, things like that. Therefore, this is one of the reasons that wireless power charging still has not been very popular for high power applications such as electric vehicle charging, is because of safety concern. So we have to develop foreign object detection method and methodology to be able to detect objects before we have these systems widely commercialized. So where are we in WPT? Well, the solution, the conclusion is that Nikola Tesla has already developed this idea 120 years ago. The microwave power transfer started in 1964. They were able to transfer some power for helicopter and solar power satellite, MPT in the 1970s. And GM introduced this inductive charger, which is strictly saying is not a wireless charger, but it's the contactless in the 90s. And high efficiency EV chargers was developed in late 2000, like 2009, 2010. And then low power chargers, consumer electronics in early 2000, it was developed and it become widely available today, starting about 3 years ago. So today you buy iPhone, you buy any of the Android phone, many of them come with wireless charging capability. In 2015, in fact, we developed this topology in 2011 until 2015. We had this publication out with LCC topology for EV charging, which provided a low-cost, high-efficiency, and compact solution. Now is a part of the guideline in the GA2954 standard. In 2016, we further developed some capacitive wireless power transfer, which is now is a foundation for many of the high-power wireless power charging, capacitive wireless power charging research. So now people are starting to develop really high power dynamic charging, real cheap applications where you can see megawatt charging capabilities in the next couple of years. The technology itself, the topology seems to be done. It is all enabled by wide bandgap devices, controls, microcomputers, materials, things like that. So major challenges right now is probably first you look at size, and we want to have smaller size, but this is limited by our electromagnetic theory. Foreign object detection seems to be an issue. Cost is still more expensive than conductive charging system. Efficiency can drop significantly if the misalignment happens and other things happens. standardization is a key issue. Interoperability is going to be critical before any of this EV or high power charging system become widely available. EMC and human safety still poses an issue, and consumer acceptance could be a bottom line to overcome. But application in specific technology is going to fly in the next couple of years, as I can see. So what are they? Well, first of all, vehicles are going to take a couple more years to realize. Probably waiting for the interoperability and standardization of OEMs to come to agreement. But if you look at this ship charging, which is a very unique application, it's going to be at the megawatt level. So this announcement was done, and this research is underway, and possibly over the next couple of years, you're going to see this electric ship development in conjunction with wireless power charging available. For trains, high-speed train, for example, may not be the best scenario for wireless charging, because when you're running at hundreds of miles per speed, and the pickup system and the transmission system could be very expensive. However, if you think one scenario is to transfer low power when the vehicle is like parked somewhere, and you power the air conditioning, the lighting system, the communication system inside the car with wireless power, that is still a possibility. Another scenario will be if the train is running into a tunnel. Right now, we have to build a much bigger tunnel than the vehicle need, because we have to have the overhead pantograph to transfer power. That cost itself can be very high. So if we build some sort of wireless power in the tunnel, which doesn't take much of space, we can reduce the tunnel size by 1/3, which means it's going to reduce humongous cost reduction. And then we'll be able to use wireless power in that short distance to power the vehicle, based also on its like inertia operating, so you don't need a lot of power. So that makes a lot of sense. So that's the application. And low-speed maglev trains, for example, or light rail. The reason you need this because the trains can be parked in certain areas where there's no power can be transferred to the vehicle. What would you do then? And then wireless power becomes a very important solution. Buses is a very important application area, because buses these days is charged like once a day, so they have to carry hundreds of kilowatt-hour of battery. They're expensive, they're heavy. The bus consumes roughly 1 kilowatt-hour per kilograms. One of the reasons, because it carries very heavy battery. If we reduce the weight of the vehicle, reduce the battery, we can reduce cost of the vehicle and also reduce maintenance. And we don't have to charge the vehicle wirelessly like everywhere. We only need to charge them at the bus stops for 20 seconds and then 30 seconds. The vehicle will get enough power to drive from one stop to another. Therefore, the bus doesn't have to stop to be charged. And it saves the cost of battery. It saves energy. Most importantly, it saves a lot of energy. Based on our calculation, it can save roughly 30 to like 100 kilowatt-hour per day per bus. That's very significant. So I think this application is probably going to be commercialized in the next couple of years. Again, wireless charging for AGVs. Why AGV? What is AGV? AGV is automatic guided vehicle. Those vehicles travel in a fixed route, and they don't have to worry about debris, because this vehicle is running on the wireless charging for just a couple minutes and they run away. But this vehicle is important. I give one example. In the seaport, this vehicle is running all day, and they emit a lot of diesel emissions, and people in those areas complain a lot. But what would you do? And you tell them, change over to electric vehicle, and they will ask you how much it's going to cost. You tell them twice as much as diesel. They say, well, that might work. However, then you tell them the vehicle has to be charged 4 hours. Every 8 hours, you have to bring them to charge for 4 hours. Then they say, oh, no, I have to buy 2 vehicles to replace 1 diesel, which means I have to spend 4 times as much money to buy a diesel. They're not going to do it because it's too expensive. But if you tell them, yes, you buy electric vehicle, you only store like half of the battery, so the cost is similar to a diesel, maybe slightly more, but you only build this wireless charging, and you're going to save a lot of money because you use electricity instead of diesel, and also you're going to reduce emission. I think they're going to buy the idea. So this is the application. And the next one is look at the underwater vehicles. These underwater vehicles does a lot of for us, a lot of work for us. But these vehicles run into the deep sea, they have to come back to be charged. And you have to seal the charging ports. It's very difficult. It takes a lot of time to go and come back. In a very long period of operation of this vehicle, what we can do is we can drop a wireless charging pad onto the sea floor. These vehicles can be charged at the bottom of the sea. And they can continue to work for many hours between charge. And they don't have to come back. It saves a lot of time, possibly 1/3 of the time. So that's good. And the next application, I'm going to talk about this. And so we all know that we have these elevators for especially high-rise buildings. Have you ever thought, where do you get electricity for the elevator, inside the elevator? Well, it's through a cable. And for buildings like 20, 50, 100 stories tall, that cable can be very long. That long cable creates two problems. One is that it will bring extra loss because it's hanging in the air. When you move the car, the cable runs with the cart, and it creates anywhere from 5% to 20% of losses of the system. So it consumes a lot of energy. Secondly, the cable over time will get deteriorated. Then we have to maintain it. We may have to replace the cable. So it's a significant cost and the interruption for the service. So think about putting this wireless system power transfer on the elevator on the side. So when the vehicle runs up and down, it receives the power automatically. And you put a little bit of battery on top of the car, so that when the vehicle is stopped in between, you still have power to power the lights, instrumentation, and even air conditioning inside the vehicle, inside the elevator. So this will work beautifully, and the cost is the minimum because you replace the long cable with this charging system. And energy savings and the maintenance savings is going to be huge. So this is economically viable. So why don't we do that, right? So maybe a few more applications, then I can stop my talk. And this one is talking about this IGBT gate driver applications. And as we know that when you have a solid transformer or solid circuit breaker, you run hundreds or even thousands of IGBTs in parallel series. Each of the gate driver needs to be isolated. So it's a problem because for many tens of, if you have a 300, let's say 300,000 kilovolt system, how would you power those gate drivers? It's a problem. So we developed this system that can transfer power from wirelessly to each gate driver system. And this study was featured actually on the ICPES Spectrum, ICPES Spectrum, the magazine. They have also a companion website. So this story was featured on that ICPES Spectrum. So it was a very interesting idea. So we use maybe a domino-like system. We have one transmitter, it transfers power to the next system, and the next system receives power, but also transfer power to the next one. You can pile up this transfer system for hundreds of gate drivers. And we also developed the technology for wireless charging of cell phones and tablets using this capacitor wireless power transfer. The cell phone you buy today is IPT, which is okay, but they're more expensive to build. So with this capacitor wireless power transfer, it can reduce the system cost. Like this one, we developed this 3D charging in a workspace or office. Your phone will be charged no matter you're holding it on your hand or you put it on desk. And we also developed this high power charging system with a company to develop this very high power, 100 kilowatts for passenger vehicle charging. Of course, it can be used for other vehicles like truck charging as well. Well, so with our study, we found that the DC efficiency can be as high as 98%. So it's dramatic improvement over the previous design. And in addition, other researchers have developed, for example, this wireless power to replace a slip ring in a double effect wind power generation systems, and motor drives in applications like drill and things like that. And I can tell you a story. In coal mining, underground coal mining, the workers have to bring, the operators have to bring multiple drills and other electrical tools, because those tools won't last 8 hours now a day. So they have to bring multiple of them down and then they bring them back to charge. Because you cannot charge, you cannot plug in anything down in the coal mine, because the electrical contact might have a spark if you plug in and out or unplug those electrical sockets. So you cannot have those. If you have wireless charging down in the coal mining, they don't have to bring that many drills down there. So it saves time and cost, right? So this is actually very useful. And there are other applications like this one, and in a rotational, like slip ring type applications, things like that. And there's also people develop this in-wheel motor where you transfer power from a stationary, like on the side instead of from the ground. So like in a parking structure or in the parking garage, you can transfer power to the wheels of the motor instead of from the bottom. And there's another application to transfer power to switch reluctant motor. So wireless power transfer. So there have been a lot of applications. Actually, in fact, my title included airplane application. Sorry, for some reason that slide didn't show up here. I'm sorry, but people have designed a system to charge drones. There are two ways to charge a drone. One is have the drone fly down to sit on a pad, charged by themselves. Other way is to actually have a laser shining to the drone, and they can be charged while they're flying. Of course, it's more difficult to have a high efficiency in that system. So in summary, WPT is an enabling technology for many applications. It is still evolving, but you might look at application for its IPT or CPT, depending whether you have enough space, whether you have concerns with efficiency, cost, things like that. Microwave, laser, ultrasound, they are studied. They're for different applications, mostly for long distance and maybe even metal barrier for ultrasound, and also for like low power applications. Safety is a major concern for high power applications. We have to develop certain technology. However, if you think about Tesla-free world, that's not going to happen, at least in the foreseeable future. Well, Tesla has dreamed of what that is not going to happen anytime soon. So a compromise among cost, safety, efficiency, and other factors are going to play in many of these applications. But commercially viable, economically viable applications like the ones that I discussed about, such as buses, AGVs, elevators, probably are going to evolve very quickly. So finally, just to show you the work that I have done. For example, we have co-authored a book on wireless power transfer with Professor Ring of KAIST, and then this is available. There are other applications available as well if you're interested to learn more. I want to acknowledge our sponsors and also our students for the hard work. So finally, I think I'll stop here. I might have a few minutes for questions if there's any. Thank you very much. So I'm going to stop sharing. Okay.
Okay. Many thanks for Professor Mi's speech. His excellent speech. Any questions from audience?
Hello, Professor Mi.
Yes, go ahead.
Okay, hello, Professor Mi. Thank you for your excellent speech. My name is Dun Fang from Chongqing Universities. I also graduated from Shanghai Jiaotong University for several years. And
nice.
It's a great pleasure for me for the also the chairman Zhang to invite me to in this conference. Thank you, Professor Mi. My research focus is on the electrified ships on the energy management of the shipboard batteries. I'm very interested on the wireless power transfers on the ship when it bursts into the position, and what is the maximum capacities for the WPT for ships?
Okay, yeah. So the ships makes a lot of sense because you're charging the vehicle in a wet area, you might have rain, water, and other things. So wireless charging can provide a very safe operation, and you don't have to wait for the vehicle to dock before you start charging. There's no limit. There's no limit to the power level. It all depends on what is available. Because the ship has a very big body, and you can install receivers on the side of the ship, and also the dock area might have a big space available. So I think you can easily build something like 100 to a few hundred kilowatts, but if you need it, you can really go on to megawatt range. There's no limit.
Oh, okay. What is the longest distance for the wireless power transfer for ships? Is there any?
Yeah, that's a very good question. For wireless power, because of the compensation, because of the resonance we have in the system. So ideally, the shorter the distance, it's better because it close to a ideal transformer. But the problem is that you can see harmonics is going to go up at a high frequency, right? So there's a certain distance, optimal distance that has to be optimized. I cannot give you a number because it was based on the size, the power level, and other the topology you choose, like whether you choose simple SS combination or you want to choose LCC. So there's optimal distance we can do, but the longest distance, I think you shouldn't go more than a few 10 centimeters. But as a rule of thumb, the size, like if I'm the pad, the transmitting and the receiving pad, should be 2.5 times the distance.
Okay.
So that's a rule of thumb. Yeah.
Okay. In this January this year, I have visited a port in Chongqing University along the Yangtze rivers, because the water levels change very evidently for the winter and the summers, and the sun ships dock very long from the berth in Yangtze rivers. So I'm thinking about the distance for the WPT. I think it's a very fantastic technologies for the electrification of maritime operations. Thank you, Professor.
Yeah, exactly. Thank you. Are there any other questions? I can probably run out of time in a minute. Yeah. Maybe we can take one more question if there's any.
Okay, you have fully addressed my concerns. Thank you, Professor Mi.
So, if I can ask a question, it seems like it's two different approaches. We can do it by wireless, or we can just change the batteries. What do you think about robots changing batteries in the vehicles?
Yeah, you're referring to battery swapping. That's actually a very good approach, but it also has limitations. It's just like any technology. You have benefits, advantage, and you have limitations. So for that battery swapping, a few years ago, there was a company called Project Better Place, and spent about $8 billion to promote battery swapping technology, but the timing was not good. So by 2015 or something, the company has to go out of business. So the battery swapping, the limitation of battery swapping is that there are a couple of issues. One is that for smaller passenger cars, it's very difficult to do because of safety related to your swapping in and out of battery, and also the limited space available. So if you go to buses and trucks, that may be a good solution because you have a lot of space to work with, and the safety may not be that a big concern again, because of the space that is available. The other limitation is that to do battery swapping, you would have to have swapping station, or you would have to have a lot of batteries available, and those batteries have to be charged. So the battery swap station could become a Mac power use site. So that may create an issue with the power company, because now you're using power in one centralized location, right? So that's number two. And the third limitation is that these batteries are going to degrade over time. So if you get a car, yes, you run the battery, but when you go back to swap the battery, if you get a battery that is fairly new, you can drive 100 miles, for example. Now, if you get a fairly used battery, you can only drive 60. So people are not going to be happy. They're going to be worried. What kind of battery I get? Do I pay actually what is worth for my money, right? So that is another concern. How to deal with the aging of the battery. And of course, lastly, is that it's a huge capital investment for the company who provide those battery swapping. It's going to be a huge cost. So who's going to do that? Who's going to pay for it, right? So that's another question. So I think it's not ruled out. Battery swapping, it has its own advantage, because for consumers, they don't have to pay for the battery; they only pay for the rent price, and it's very easy to do things like that. But the limitation I mentioned about 4 limitations, I could hinder the development of this battery swap.
Yeah, thank you for a very interesting presentation.
You're welcome.
Okay. Thanks again for Professor Mi's excellent speech. Let's move our next speech. The next speech is from Professor Etsu Kawamura. He is the ICPES Fellow from Yokohama National University, Japan. His speech title is Challenge to Realization of 99.9% Power Conversion Efficiency Inverter and its Application Field.